Question 10 is just plain tricky. It's not hard, it's tricky. It tests your understanding of heat gain equations and how they relate to simple facts about air handling systems. The core of the question is never asked or even hinted at, but it reveals itself once you've given the question any critical thought. Initial critical thought solution elements. 1. What are you solving for? The required CFM for an airflow serving a load. 2. What is the fundamental process? Heat gain for one single airstream. 3. What are the first considerations to find the solution in connection to the fundamental process? Finding what variables are available and what variables are impossible to get. 4. Are there key assumptions? The supply air temperature given is dry bulb. It should seem obvious from first reading the question that some sort of heat gain calculation will need to be done. You're given various loads and temperatures and asked to solve for the CFM of airflow. But what heat gain calculation is needed? That's the tricky part. Before ever worrying about the altitude, start by considering the loads. Both sensible and latent heat loads are given. But you should know that a total heat load is the sum of sensible and latent heat loads. So there are really 3 loads. And there are 3 standard heat gain equations. Without knowing more or thinking more about the question, favor solving for total heat gain because it captures both loads in one. In order to solve for total heat, determine the change in enthalpy. So, establish the enthalpy values of everything possible. But to understand how they change, set up your diagram like this. Look up the enthalpy for the outside air and the room air on a psychrometric chart based on the information given in the question. You must determine the supply air enthalpy. But is that possible? Without knowing the CFM, the amount of mass flowing is unknown. So a mixed air calculation for air here isn't possible. And it's clear that the 2 airstreams are passing through some type of heat transfer equipment and not just merely mixing. It's clear because 55 degrees isn't between 75 degrees and 95 degrees. This mixture must be hotter than 55 degrees because the mixed air temperature always lies on a straight line between the mixing airstreams. So, the total heat gain equation has 2 missing variables, CFM and delta H. Some other solution path must be found. This video is brought to you by ExOverZero, which offers CBT practice exams. Your only chance to get practice at computer-based testing is to use the link below and download. Perhaps if you can't solve for both the sensible and latent heat in one total heat equation, they can be solved for individually and then combined. 2 loads, 2 calculations, 1 final CFM for the answer. But wait, does that make sense? Of course, it's possible to add the 2 loads together to get the total load. But can the CFMs be combined together to get a total CFM? From an air handling and equipment perspective, consider that there is no such thing as sensible heating ducts or latent heating channels. Airstreams aren't divided up like that. One airstream goes through sensible and latent heat changes, and there is only 1 CFM to solve for. But there are 2 types of loads within the same airstream. You can mix 2 airstreams by combining their individual CFMs. But you can't mix 2 types of heat gain by combining their individual CFMs. From an equation perspective, consider that if you split them up and solve for one type of heat, sensible or latent, first, and then solve for the other type of heat, you'll then be forced to go back and change the CFM value in the first solution by adding in the second solution. But that changes the first solution, which means the first solution isn't correct. Stop and think about this logically. Wanting to combine the CFMs into one means that there is, and there has only ever been, one airstream. Follow this train of thought. If the CFM required for the sensible heat gain can be determined, and there is, hypothetically, added CFM for the latent heat gain, then the CFM used to solve for the sensible heat gain is too low. So, you can't determine the CFM required for the sensible heat gain after all. This is the tricky part of question 10. Knowing that there can be two types of heat gain in one airstream, and that doesn't change the one airstream's CFM. Solving for one type of heat gain means that's the CFM for the other type of heat gain. An important note on this fact: there is only one CFM and one airstream when considering the types of heat gain. Remember, a single airstream, when heated or cooled, can change volumes so that one airstream may have two different CFMs at different times. But one airstream is not made up of different CFMs that are associated with different heat gains at the same time. Dry bulb temperatures are given in the problem, not humidity ratios. So, use sensible heat gain to determine the total CFM in the airflow. Refer to the NCEES Mechanical Reference Handbook, Section 9.1.7, to see the sensible heat equation and the sensible heat factor for 5,000 foot altitude, which is 0.92. This difference in temperatures should be obvious. 75 degrees minus 55 degrees. That's the difference between the room air and the supply air. Looking at this diagram, it's clear that it can't be the difference between the outside air and the room air or the supply air. Have the conversion between tons of refrigeration and BTU per hour memorized. This equals 15,000 CFM. Option C. To get good at questions like this, you should be able to quickly reference the NCEES Mechanical Reference Handbook, which will be your only reference material on test day. You can't do that by just reading through it like a novel. Get good at it in the only way possible, by looking lots of stuff up in it. ExOverZero gives you the opportunity to do just that in a drill book for the NCEES Mechanical Reference Handbook. Use the link below to purchase.